Um, okay, so why don't we go ahead and get started? It's a few minutes after. I know that there's people still coming in, but I'd like to go ahead and give Andy as much time as possible. So let me go ahead and stop my sharing and go on the screen here. And hello, everyone. Thank you for joining. I know that we have a couple of things going against us here today. So a couple technology issues. Again, I apologize. We're trying to work through the Google Live transition, and sometimes it's given us a little bit of a headache. So thank you for that. Today, we're at a special time. I hope this works out for everyone, but we're trying to do it a little bit earlier so we can have Andy join us, and I think it's well worth it. So today we have Andy, who's going to take us through Meteorology 1 today. Actually, Andy is in Stockholm, and he is a super smart guy. He's a particle physicist. He's a meteorology guy, and he's also a teacher. So I hope that you get a lot out of this session. For those of you who are on the Google Live page, there is the live chat where you can enter questions. And for those of you who might pop on the participate link, we do have the chat room in there also. And for those of you who are on the view and would like to join the participate, we have plenty of room. Obviously, you can see it's just Andy and I right now. So I did put a link for today's slides into the chat session. And I think every once in a while as we go through, I'll go ahead and repaste that in there just in case people missed that. So Andy's going to go ahead and have the slides presented behind him. You can see he's in a classroom setting. So you'll be able to see the slides behind him. But we wanted to go ahead and have a link to the actual slides in case you want to follow along with us. So with that, it's 5 after the hour. Andy, I'll turn it over to you. Thank you very much for leading this session. And I know as part of your slides, you have a little introduction so you can explain a little bit about yourself. So it's all yours, man. Thanks a lot.
Thank you very much. It's a pleasure to be here and a pleasure to talk to you guys about something as important as weather. This is Meteorology 1. My name is Andy Kravlich. Why should you listen to me and my ramblings? Let's go to a little bit about myself. And as Chris said, he's going to post the link to the slides so you guys can follow along on your own computers and not have to bring yourself to advanced levels of myopia by following along. We got some 50 slides to go through, so this is going to be at somewhat of an advanced speed, but don't worry, it's all going to be recorded and you can be able to watch it in the archive later on. My name is Andy Kravlich. I'm 35 years old and I live in sunny Stockholm, Sweden. My educational background, I have a master's degree in physics, field and particle theory from the University of Stockholm. I did, as a part of that, 1 semester of post-grad meteorology studies where we did some computer modeling and forecasting and so on. Very exciting stuff. After that, I got a teaching degree from the Stockholm Institute for Education and worked as a physics teacher for 5 years before transitioning into the IT sector where I work today. Besides being an IT guy and a pilot, as you can see, I am also a singer. So I am no stranger to appearing before people in all kinds of settings, educational or entertainment based. Now let's talk about the sources we're going to be doing today. We got the FAQ, which is, I'm sure, familiar to anybody who's into aviation theory and looking for this FAA resource. I got a couple of links to the same material right there in the presentation. So if you haven't found it, that'll be chapter 12 of the FAQ, and you're welcome to click on that right now. Now, my image of the atmosphere, even when I was a kid, I had the image of the atmosphere as a lava lamp. So I'm just going to get this seductive video to start playing behind me. And my image of the atmosphere was always this. This is how I imagined. You know, people say that Dale Earnhardt could see the air, and that's why he was so good at drafting people in NASCAR. Well, I could kind of see the air like this. You know, I always thought of air as big, transparent bubbles of mass moving around, you know, with different temperatures and different pressures running into each other, sliding over top of each other. And the atmosphere kind of always worked like that for me. And because of that, I think I understand the atmosphere in a different way to what some people do. And I hope to give you some of that understanding today. It starts pretty simply. It starts with what I call the lava lamp laws. The lava lamp laws are the three of them. Number one, hot stuff rises. Hot stuff rises, which means that the bubbles in the lava lamp go upwards. And what goes up must come down, which means that once they've cooled off at the top, they come right back down and they're replaced by other bubbles, which are warmed by the heating filament in the bottom and are rising towards the top. The third lava lamp law, nature abhors vacuum, basically says that as soon as this lava lamp bubble is coming up, it's not leaving a vacuum behind it, it's leaving behind a space which something else is going to rush in to fill, whether that's another bubble or the transparent medium, whatever. But it's all about constant motion, heating, rising, cooling, falling, and so on. So that can drive a very advanced understanding by a very simple model of the atmosphere. So most of what you'll see, even as far as thunderstorms and so on, is basically just going to be that simple activity played up in a huge scale. So what is weather? I decided that if we're going to talk about weather, it's best to perhaps define what we mean with the concept of weather. And weather is basically just the behavior of air in the atmosphere of the Earth. Now, I've put down a definition right here, which is differences in air density, which are caused by changes in air temperature, result in changes in air pressure. And this creates motion in the atmosphere. And this motion causes the moisture content in the atmosphere to change form from one to the other, from vapor to liquid to solid, back to liquid, back to vapor. And that is what we call weather. It's motion, moisture, moisture uptake, moisture discharge. It's very simple, but it boils down to four basic concepts: air density, air pressure, air temperature, and air moisture content. So we're going to attack these things in three separate stages. Density and pressure is kind of one thing, and then we're going to talk about temperature, and then we're going to talk about moisture content. And then we're going to slide it all together and see how air masses and fronts and so on are formed. So starting with pressure and density, when we talk about air pressure, it's kind of difficult to understand what we mean. We tend to think of air as a vacuous medium, as something which doesn't really have any weight, any mass. We move through it very easily, but as I usually tell people, all you have to do is roll down your window in your car when you're moving along and stick your arm out, and you'll find out that air actually has density. You just can't feel it at low speed because it's so low, the density. But as you start approaching a higher speed and you put that hand out there, that hand is going to start compressing the air molecules, and they're going to fight you. They're going to impact the surface of your hand, and they're going to push you back. So there's definitely air all around us. And this air also has weight. It has mass. And to be honest, there's a lot more air above us than we sometimes think, because the atmosphere, we know that if somebody wants to go to space, they have to go over 100 miles into the air. There's 100 miles of air above you right now, and 100 miles of air, 100 miles of something very vacuous and very light is still a lot of weight. And if you basically put an imaginary scale on the ground and had a 1-inch square column of air that stretched all the way out into outer space, it would actually weigh 14.7 pounds. It would weigh 15 pounds, so 15 pounds of almost nothing. And this is what we call pounds per square inch. In Europe, we don't use this system. We have the metric system, so we use a unit called hectopascal, which is equivalent to the unit millibar. And the atmospheric pressure is 1,013 hectopascal. This is what the tower will call out on a neutral pressure day. And of course, anybody who has an instrument, hello, an instrument in their planes in America will know that you don't set it for PSI. You set it for so-called inches, inches of mercury. So 299 or 29.92 inches, which you set onto your into your Colesman window in your altimeter. Now, the pressure of the air at a given place and at a given time, of course, isn't going to be the same all the time. Now, I said 14.7 pounds per square inch, 1,013 hectopascal, 2.9 or 9 or 2, but this changes. This changes with air temperature. It changes with altitude. It changes with density. The pressure at the bottom of a dry lake bed isn't going to be the same as the pressure on top of Mount Everest. The pressure on a hot day isn't going to be the same as the pressure on a cool winter day. So to combat this, we humans did what we humans tend to do best, which is standardize, which is make up models and make a standard model of something which we need to reference later on. So we decided that the optimal atmosphere, the international standard atmosphere, is this, which is behind me right now. That's 1013 hectopascal, or 2.9 or 9 or 2, 15 degrees centigrade, or 59 degrees Fahrenheit, and it is at sea level. So if you ever find a day like that, you got 1013 hectopascal, or 2.9 or 9 or 2, 15 degrees, 59 degrees Fahrenheit, and you're at sea level, and you trap that air in a bubble, that is your international standard atmosphere air. That is standard air. As you can imagine, we very rarely have standard air. It's something which is a theoretical construct, and it's very difficult to get a hold of, and if you could, it would be sold by the pound. So we need to kind of figure out how air pressure is affected by things like temperature and altitude and so on, so that we can translate this international standard atmosphere pressure into what the heck is actually going on. Now, air gets less dense and air pressure decreases the higher we go. Most people have an understanding of this because we realize we need spacesuits. And we realize the guys in the U-2 plane need pressure suits. We realize that an airliner needs to be pressurized. We realize that if we fly over 10,000 feet, we need oxygen after a certain amount of time. We realize that people who climb tall mountains need to have oxygen equipment. And we realize that we down here near sea level don't need any of that. So there's a kind of an instinctive understanding that air gets thinner as we go up. But why is that? Why does air get thinner? This is the difference between a scientist and just a normal person. A normal person will just say, okay, air gets thinner. A scientist will go, why? Why does air get thinner? You know, can someone explain that to me? And how much thinner does it get? Well, it just so happens to be something which a law invented by or discovered by Newton explains. It's the gravitational law. The gravity between two objects is decided by the radius, or the range between them, squared, inversely proportional to that. So if something gets twice as far away, the gravitational force pulling it is going to be 1/4 of what it is if it goes half the distance. So the closer something is, the more gravity attracts it. So to start with, air molecules which are closer to the surface of the Earth, and therefore closer to the center of the Earth, are going to be slightly more attracted than the ones that are higher up. So they're going to be a little bit heavier. And as they get heavier, they get closer to the ground. And as they get closer to the ground, they get even heavier. And as they get heavier, they get closer to the ground. As they get closer to the ground, they get even heavier. And that continues until they basically hit the atmosphere. And these molecules are whizzing around every which way, bumping into each other, because air has a lot of kinetic energy. It's like 1,000, drunken kids just running all over the place and pushing the boundaries and pushing on each other. And so all this air that comes in from the top is now finding that it can't go all the way down, because once it gets to a certain altitude, it starts getting, bumped by the air underneath it. And the air above that can't get all the way down because it's getting bumped by the air underneath that. And what happens is layer upon layer upon layer of air starts compressing, and it creates this compression effect, which makes the air at the bottom of the atmosphere a lot thicker than the air as we go further up. Now, this effect, as I said, is exponential. It's inversely proportional to the square of the distance from the center of the gravity of the Earth, which means that as we get further and further away, the gravity is going to decrease, not just linearly, it's going to decrease like that. It's going to drop off pretty sharply. But at our low altitudes, we can kind of make a linear approximation of that. So most of the time, it's going to be correct. And the decrease in pressure with altitude is about 12 hectopascals for every 100 meters. And everybody who just fainted because I'm using the metric system, or Système International, as they say, that corresponds roughly to 1 inch of mercury for every 1,000 feet. So I'm going to say that again. It's 1 inch of mercury for every 1,000 feet. Now, as I said, that doesn't apply to the entire atmosphere. It only applies at low altitude, but it's an approximation we can live with because that's the places we usually fly. Pressure and density are very important towards keeping an aircraft flying. Our engines breathe air, our wings push against air, our flaps deflect air, and our whole airplane is based around being in the air. So the qualities of the air around it affect this very much. I'm not going to go into depth here because you guys are going to be doing weight and balance. You guys are going to be doing, performance calculations. But just to say that the density and the pressure of the air around you is going to affect greatly the way that your aircraft behaves in the air. It's going to affect your engine performance. It's going to affect your takeoff performance, your takeoff roll, the ability to clear obstacles, the rate at which you climb, and so on. And as I said, it doesn't only depend on altitude, it depends on things like moisture and pressure as well. So you're always going to need to make sure that the atmosphere that you exist in that day can actually support the power and the takeoff performance which you need out of your airplane. It wouldn't be the first time if you ever got to a situation where you could land at an airport, spend the night, and then the next morning it's 20 degrees hotter and you find that you can't take off from that runway anymore because you could the day before, but because it got hotter, the air got less dense. And because it got less dense, there's less air for the engine to breathe, less air for the wings to push against, and suddenly you find that you're not able to take off, if you're lucky. If you're not lucky, you didn't do your calculations that day, and you find that out as you are climbing out on the wrong side of the power band, basically flying like this, praying to God that your full power is going to get you out of there. Bad idea. So always do your performance calculations before you take off. That could save your life someday. Some important notes about altitude and pressure. We define altitude and pressure in a couple of different ways, and it's important to know what we're talking about. So if you ever hear the tower talk about QNH, ATIS will do that all the time over here. They say QNH is 2994, QNH is 2785. Well, what is QNH? We'll start with the original measurement which people used, which was QFE. QFE was the pressure in the Colesman window on your altimeter when you were basically at your runway and you set the altitude to 0. So whatever elevation the runway had, even if it's at the top of Mount Everest, you set that as 0. And then the pressure that's in that Colesman window, that's your QFE. That's your equivalent pressure. The problem with that is it's only really valid for one runway. As soon as you fly somewhere else, which has a different elevation, well, they're going to have a different QFE, right? Because they have a different elevation. So your altimeter isn't really going to work. And they could send you a QFE over the radio and you'd have to, set it up. But then, of course, what happens if one aircraft takes off from one airport and another one takes off from this airport, and they've both got the same QFE, but how do they know where they are in relation to each other? They're not, because their altimeters are going to be set completely differently. They might think they're at a 500-foot separation, but they're actually just about to run into each other. So that's a bad idea. We realized that quite early on, and we switched to something called QNH. QNH measures everybody's altitude from sea level. So basically, if you took a line around the Earth, which was basically at sea level for the entire globe, whatever altitude your airport was over that imagined sea level line, that's what it says on your altimeter. So if you're at the top of Mount Everest, it would be the altitude of Mount Everest, the height of Mount Everest. It wouldn't be 0. The advantage of this is that two airplanes which take off from different airports can at least be in agreement about what altitude they're on, because they're basing their altitude, their 0, on the same altitude, which is sea level, 0. So that's just a quick note about that. Going on to this pressure differential, let me back it up a couple of slides and say, if you guys remember, that we had roughly 1 inch of mercury for every 1,000 feet is how much less pressure there is as we rise. Okay, so if it's 299 or 2 at sea level, it's going to be 1 inch less, 289 or 2 at 1,000 feet, 279 or 2, 2,000 feet, 269 or 2, 3,000 feet. You get what I'm saying. Here's an illustration of that same principle. If we've got New Orleans here, New Orleans is basically at sea level, and we could try to, for jokes, calculate the altitude of Denver Airport. If we know that New Orleans is reporting 299 or 2, and we know that Denver is reporting an air pressure of 249 or 2. So 299 or 2, 249 or 2, the difference is 5 inches. And if it's 1 inch for every 1,000 feet, well, Denver should be at about 5,000 feet of altitude, right? Well, the altitude of Denver Airport is 5,130 feet. They call it the Mile High City for that reason. So this is one way that you can determine the altitude of things by the pressure change. And this is one of the ways in which they asked us during one of our physics papers to determine the height of a building given a barometer. So basically, we went up to the top of the building, measured the pressure, and applied this rule, and we could tell how high the building is. This is how your altimeter works. This is it's not rocket science. Before I go on to temperature, are there any questions with regards to air pressure? I know I'm kind of running through this because we have a lot of slides to get through, but I'd just like to take any questions if there are any at this point.
No, I don't see any, Andy. I think you're doing an awesome job, man.
Cool. Well, I'm happy.
Keep going.
All right, great. So let's talk about temperature. Now, we said pressure, density, temperature, and moisture content. Those are the 4 key areas that help us determine the behavior of weather. Now, temperature changes with altitude as well, just like pressure does. And I think we also have an idea that air gets colder the higher we go, right? Because it can be sunny and nice in the valley, but there's usually snow in the mountains. So the higher up we go, the colder the air becomes. How much colder? Well, that's for this lovely equation here. This is the ideal adiabatic lapse rate equation. But if we don't want to do that calculation, we can basically give it a rough value, again, of about 2 degrees centigrade or 4 degrees Fahrenheit per 1,000 feet. This number varies. Again, we rarely exist in the ideal atmosphere. It goes somewhere between 3.5 and about 5.5 degrees Fahrenheit per 1,000 feet, but 4 is a good approximation. It's true in most cases. So just like we did with altitude, we can do little calculations. If the temperature at sea level, for instance, is 70 degrees, we could ask the question, what is the temperature at 6,000 feet, given a normal international standard atmosphere? And it'll be 70 minus the number of the 1,000 feet times 4. So it'll be 6,000 feet, so 6 times 4, 24. 70 minus 24 is 46. We know the temperature is going to be 46 degrees at 6,000 feet. Now, this is going to become important later on when we start talking about moisture content, because that'll help you do things like calculate the cloud base and maybe even the percentage of risk for icing and things like that. So it's one of those important formula that you can keep in the back of your head, which other pilots may not know about, and that might help you minimize the risk. Temperature decreases with altitude. I just said that because we had snow at the top of the mountains. This isn't strictly true. It's true in our little portion of the atmosphere here where we do most of our flying. Most of us GA guys are going to be below the level of this commercial jet over here. So we're going to be like over here flying, and the guys who are flying the big rigs, they're going to be up here. But there's still a lot of atmosphere left. So when we say we talk about the behavior of the atmosphere, we're really only talking about the behavior of what we call the troposphere. The troposphere is basically where all the weather happens. It has to do with the word tropic. So troposphere is where the weather happens. Above the troposphere is something called the tropopause. You'll see this is a dotted line over here. And the tropopause is something very interesting. Starting at this level, air no longer gets colder as we rise. It starts to heat up again. And you can ask why and how, and that would be a legitimate question. Well, it's basically cosmic radiation and radiation coming from the sun, which is absorbed by certain chemicals and certain gases in the higher levels of the atmosphere. But just to understand the fact that the air doesn't perpetually just get colder and colder. There's this image that as you get higher and higher, you get into the cold reaches of space. That's true, but before you get there, you have a couple of temperature spikes to negotiate as well. So just so we understand, when we talk about the atmosphere in this course, we're only talking about this part of the atmosphere, because unless you guys are flying for SpaceX or about to embark on a U-2 plane, you're not going to be up here anyway. So let's keep it simple. Just get set up here with my next slide. So I just mentioned that the heat is coming from cosmic radiation in the sun. A question I asked when I developed my lava lamp theory of the atmosphere is, well, it's a little weird for me because the lava lamp is heated from beneath by a little filament, which basically heats up the water and makes the current flow in the lava lamp. But the atmosphere isn't heated from beneath, is it? I mean, the sun is above us. It's not underneath us. So how can all of this convective motion start if the heat is coming from up there? Well, it turns out that for the most part, air, the normal air that we breathe, is transparent to the radiation coming from space and from the sun. It can't interact with the air. The air doesn't understand that the radiation is there. It doesn't feel that the sun is hot because the radiation from the sun passes right through the air. It's transparent. In fact, this is why we can see the sun, because if the air was interacting with the radiation of the sun, it would change the radiation of the sun. It would absorb the radiation of the sun, and we wouldn't see as much of the sun as we do. The very fact that we can see at night and we can see clearly enough to have telescopes and so on is because of the fact that air interacts so poorly with light. But the ground interacts really well with light. The ground interacts really well with the sun's radiation. The ground gets really warm by the sun's radiation. And guess what? The way the ground lets out that radiation, that's what the air can pick up. That's the convective motion source right there. So you could say that the ground translates the radiation of the sun into something which the air can understand and interact with. So the ground is like a battery which charges during the day, discharges during the day, constantly and continuously. And that's what keeps the atmosphere going. That's the reason why the atmosphere acts like a tea kettle, where the heat is coming from the bottom and the convective motion starts from the bottom and flows in this direction, just like it does in the atmosphere. Really beautiful mechanism for which we should be grateful. Otherwise, the top layers of the atmosphere would be really hot, and we would be stuck in a perpetual winter down here with no ability to see anything. So I'm really glad that air has those particular physical qualities. If we look at the planet, it tilts at a 23.5 degree tilt to the ideal axis of the solar system. So that means that as it goes around, we have seasons. Certain parts of the Earth are more exposed to sunlight. Certain parts of the Earth are less exposed to sunlight, summer and winter. But there's an area in the middle which is kind of always exposed to sunlight, because that 23-degree tilt isn't enough to ever really tilt it far enough away from the sun for it to be unreachable, for there to be winter there. So there's these really hot areas in the middle of the planet which never have time to cool off at night, because there's so much energy being stored there during the day that it doesn't really get cold enough at night for them to have to kind of start over the next day. And that is the source of really large convective motions here. So we start with, the hot air starts to rise here, and it goes over there, and then flows towards the colder regions on the pole, cools down, and as it cools down, it falls down here. So we get cold air coming down here, hot air coming up here. And as this hot air is moving, it's getting replaced by other air which is rushing in to fill that hole, just like in the lava lamp. So that means that the whole Earth is in constant motion. The atmosphere never stands still. As soon as there's a warm spot, there's something rising out of it. As soon as there's a cold spot, there's something falling into it. And if something rises, something else comes to fill it, the space that it leaves behind it. If something is falling down, it's displacing something. So all of these things lead to an incredibly complex system. And the fact that we can forecast weather at all, I would say, accurately, is a modern miracle. In fact, we use supercomputers on this planet for two main reasons. Number one is cryptography, to break really hard passwords, signal processing, and the other is weather forecasting. Because every time we make a model, we have to basically figure out how a small portion of the atmosphere, like for instance, upper Seattle, is going to be based on the convective motions of the entire planet. You know, because if there's a storm somewhere else, it's going to affect how much sunlight the Earth can grab that particular day, because the clouds are going to be in the way. And that's going to affect how much convective motion there can be, because the ground isn't as hot as it could have been otherwise. And that's going to affect how that air, which was supposed to go out from there, isn't going to do that. And that means that air from here is going to do it instead. And that means that there's going to be something completely different going on. And that means that your forecast for Seattle is just borked. So as a rule of thumb, I usually approach weather forecasting with a very careful eye. So if I'm looking at something 4 days in advance, I'm just basically going to be looking at, is it going to be high or low pressure? Is it going to be, you know, do they think that it's going to be rain or anything like that in the 3 days like adjacent to that? As we get closer and closer, the forecast becomes exponentially better and better, because there are fewer decision points that can go wrong along the way. And to be honest, I never make my go, no-go decision until the morning of the very same day, because you never know what happens at night. Nights are crazy in meteorology terms. Half of the time you make a really wonderful forecast, you go to bed, you wake up the next morning, and something happened during the night. Some, air mass got displaced, and suddenly that storm, which was heading your way, is going to be 100 miles south of you. And you had no idea because you were sound asleep. So I always look at the weather the day of the flight. Never accept a 3-day forecast and go, it's going to be cool on Tuesday, so I'm just going to make my decision here and now. You got to stay on top of that thing. So I need to talk about something which is kind of advanced, but which informs the entire behavior of winds on this planet. So stop me if I get ahead of myself here, but we need to talk about something called the Coriolis force. I know you guys usually say Coriolis, but it's a French scientist, for goodness sake. His name was Coriolis, so let's call it Coriolis force in his honor, lest they call our former president George Bush and so on. Coriolis force is basically a very, very simple thing. Most people do these graphs where straight lines turn into curves, and they don't really explain it. All Coriolis force is the rotation speed of the Earth helping you along as you move. Did you ever wonder why we launch rockets from Florida? Why the European Space Agency launches them from the Amazon rainforest? Or why the Soviet Union launched them from Baikonur in Kazakhstan? Not in Siberia, not in Alaska, not in northern France? It's because these areas are closest to the equator. Because the Earth is a ball, as it spins around, its perimeter spins at a certain speed. And the further you go towards the equator, the faster the speed actually is in terms of miles per hour, because it has to make a revolution in 24 hours regardless. If you're standing on the North Pole, you don't need to be moving at all. You can stand still and make a revolution in 24 hours. If you're halfway through, you're going to be maybe going about 800 miles an hour. And if you go towards the equator, you'll be doing over 1,000 miles an hour. Now, isn't a 1,000-mile-an-hour boost really cool when you're trying to launch a rocket? Well, yes, it is. And that's why we launch rockets from as close to the equator as possible. The rotation speed of the Earth gets bigger towards the equator, the rotation speed increases. And so it helps you launch that rocket into the optimal trajectory. But that only works if you're launching it in the direction of the rotation, right? If you try to launch it the other way, then the rotation speed would be working against you, right? So it's either working completely for you or completely against you. But what happens if you try to launch it straight up or straight down? Well, something very interesting happens. If we switch to the next slide, if you launch from this point, which is the European Space Agency's launch pad, and you go straight north, and you try your darndest to go straight north, you'll find that your rotation speed over here is helping you out 1,000 miles that way. And if the ground underneath you isn't also moving at 1,000 miles an hour that way, you won't perceive it as being over the same spot on the Earth anymore. Because as you go up here, this part of the Earth actually has a slower speed because it's smaller. And this part of the Earth has an even smaller speed, all the way up to the pole, which has no speed at all. That's great.
You're having technical difficulties as well. Good.
Technical difficulties are an international phenomenon. So that basically means that even if we try our darndest to go straight north, we're going to find out that because we have this giant 1,000-mile-an-hour speed boost, we're actually going to be doing this. It seems counterintuitive as heck, unless you really think about it, because I'm actually moving, the speed of the rocket here plus 1,000 miles an hour this way. This guy over here is just moving maybe 300 miles an hour this way, because the Earth is way smaller where he is and still makes that 24-hour revolution. The day is equally long here and there, so this place has further to go to make it in 24 hours. So the speed boost that it gets from its own rotation means that it's going to go this way. And if you try to launch it south, it's going to go this way. It's going to go into the direction of the rotation. Coriolis force is a very counterintuitive and difficult thing to understand, and I completely understand if you guys don't understand it. This is why we have myths like this. Coriolis force affects, long-range artillery and navigation. It affects current formation. It affects weather systems. It doesn't affect things like your sink or your toilet bowl, because, to be honest, you need to have an appreciable difference in the rotation speed of the Earth where you are. You need to have, 20, 40, 60, 80 miles to calculate across for you to even be able to pick up a minuscule difference in that. If we're talking about 20 inches, forget about it. I mean, we're on the 7th decimal, so it's going to be imperceptible, and it's going to have to do with the construction of your bowl. So you have to remember, this is a very small, imperceptible thing. But weather systems are huge, and imperceptible things over huge systems can still have an appreciable effect. The next thing we're going to talk about is pressure systems. We'll come back to Coriolis force in a while, because we're going to need Coriolis force to understand how pressure systems communicate with each other. But pressure systems are really interesting. They talk about high and low pressure regions in weather forecasts all the time. They say, well, there's going to be a region of high pressure over this area, and there's going to be like a low pressure region here, and there's going to be a front between them, and so on. What does that mean? How can there be a bubble of air which is at higher pressure than the air around it? Why doesn't the pressure just equalize itself? Well, it's not like a stationary bubble of air that's at higher pressure. That would need some kind of container around it, or it would literally just equalize itself. The pressure is due to motion. High pressure happens because of cold weather. Cold areas usually have high pressure. It means that air is falling into these cold areas. Remember when we talked about the convective motion, how the air would get colder and fall back down and displace something? Well, this is what happens. Colder areas, the air falls down, compresses. We were talking about the compression effect before. Compresses the air underneath, creates an area of high pressure. And this high pressure area makes things want to get out of Dodge in every direction. So the air is basically escaping this high pressure area. Low pressure is what happens in those warm areas, which we were talking about before. So you get the warm area, the air is rising as it gets, as it gets hot on the ground. You get that lava lamp effect, and the air starts to rise, and other air rushes in to fill that. Okay, so as the air starts to rise, there's like a little bit of a vacuum here. There's low pressure, and other air rushes in to meet it. All right, so high pressure areas are areas where air is falling down. Low pressure areas, Air is going up. That's how I want you to think about it. Now, if we think about how a high and a low pressure area communicate with each other, because they need to do that. As I said, they can't just sit there and be at high and low pressure. This pressure is going to want to even itself out. Well, the high pressure area, where air is falling down, is going to want to generate these winds that are going all directions around it out of the high pressure area. The low pressure area is going to want to suck wind in so that it can start to rise. So that's going to suck in wind from all over to this area right here. Because of Coriolis force, because of that wave off that winds get as they go north or south or even a little bit east and west and so on, you're never going to get a straight shot from a high pressure system into a low pressure system, because these two are so far away from each other that it's not going to be like your toilet bowl. There's going to be a difference in the rotation speed of the Earth, the circumference of the circle where you're in right now. And as this wind goes from the high pressure area towards the low pressure area, it is trying its darndest. It wants to go this way. It wants to go straight to the low pressure area. It goes, I'm desperate to go here because this is where the low pressure is. But it can't, because it's got this rotational motion because of the Coriolis effect, and it can't help itself. It starts to fade off this way. The same thing happens to air that's going into this low pressure region. It's trying its darndest to go straight into the low pressure region, but it can't. As it goes in, it starts to fade off to the left. It's because of the Coriolis effect, because of the rotation of the planet, because the planet gets bigger in the middle and smaller toward the poles, and these systems are so far away from each other that the wind can't just flow from one into the other. It necessarily needs to do this because of the Coriolis effect. It's not trying to do it. It's a side effect of what happens because of the nature of the Earth. The cool thing about it is we can use that as pilots, right? So if this high pressure area over here is generating these winds that basically go off in this direction, and this low pressure over here is going to generate these winds that go like that, well, it doesn't take a rocket scientist to figure out that if you fly between them in this configuration with a low pressure on your left and a high pressure on your right, you're in tailwind city. You're going to have tailwinds all the way, because that's the way the Coriolis force sets it up in the northern hemisphere. The air has no choice. As long as you set up your flight plan so that the low pressure is on your left, high pressure is on your right, you don't ever have to worry about a headwind. You're never going to have one. That's just the way the atmosphere works. So there's a way that weather people show this region, between the high and the low pressure. We try to show it with lines where we show exactly the same air pressure. So where geographically the same air pressure would be found, if you could draw like an ideal line and say, well, this has 2.9 or 3.4, and where else are we going to find 2.9 or 3.4? We're going to find it along this line, and then there's going to be 2.9 or 8.5. That's going to be at a different line, and so on. We call these lines isobars. The cool thing about isobars is they tell us loads of stuff. Wind, because of the effect in this previous picture, it goes this way. Wind goes parallel to these isobars, because as this high pressure region is trying to dump out all of its air, all that air is going to start spinning like that. And the wind is going to go parallel to these isobars. So that tells you something about wind direction. And remember, if you have the wind in your back, that means the lower pressure is on your left, high pressure is on your right. The Coriolis force balances out this desire of the high pressure air to go toward the low pressure. It fades off, and it actually starts going perpendicular to its original flight plan and parallel to these isobars. And that's why we create these cyclical weather systems which never seem to be equaling themselves out, because the air which is trying to go to the low pressure system just ends up going in circles. And that's why we can get stable areas of high pressure or stable areas of low pressure without them, bleeding out into each other as they would without the Coriolis effect. Now, close to the ground, this is really important. Close to the ground, there's going to be mechanical turbulence. I have a picture of that right here, Basically, the air snags on all sorts of objects around here, all sorts of objects which are in the way, houses, trees, forests, and so on, which catch the air as it's trying to do this cyclical motion. And the Coriolis force is lessened because of that. It can't really act as strongly as it wants to. So air at altitude is going to have a stronger Coriolis force than air at the ground. We're going to see this by the air at 2,000 feet, approximately when we're out of this mechanical turbulence layer. It's going to have a 20 to 40 degree different direction to the right as compared to air on the ground. So that means if the air on the ground is going, 360, air at 2,000 feet is going to be 020 or 040. That's something to plan for when you guys are planning your flights, or when you're looking at a headwind or a tailwind or a crosswind into a landing situation. You should realize that windsock is in the lower region, and if you want to extrapolate that wind to 2,000 feet, we'll add about 20 to 40 degrees because of the Coriolis effect. 20 to 40 degrees is going to be the wind at altitude. This means that as you get closer to the ground, the wind is going to deflect by 20 to 40 degrees in the middle of your setting up your landing pattern. And you need to keep that in mind. Now, a lot of people say you should pick a crosswind from the right, crosswind from the left. If you're landing, if you have a direct crosswind, I'm just going to give you the meteorologist's point of view and leave it at that. So we're not going to do that debate today. The meteorologist's point of view is that because of this 20 to 40 degree shift to the right, landing into a left crosswind is better from a meteorological perspective, because if the wind gusts, it'll turn to the right by 20 degrees, and wind at altitude will turn to the right by 20 to 40 degrees. So that means that if you have a left crosswind at altitude, it's actually going to be a little bit of a headwind. And it means if you have a direct left crosswind and you're setting up for a landing and the wind gusts, because the gust overcomes the mechanical friction of the stuff that's in the way, wind is going to go to the right. So it's going to go a little bit into a headwind. If you land with a direct right crosswind and the wind gusts or at altitude, you're going to be landing with a little bit of a tailwind. So aviation decision making, if you have a left base and the base is going to be short and so on, whatever, you guys keep that in mind. But that's one piece of information which could inform your decision making in a situation like that. So let's talk about that lava lamp phenomenon. This is basically what happens in the air. You get, dark patches of ground which create these big bubbles of air which go up. We call these thermals. And one of the easiest places to find these thermals is a parking lot. This is me landing at Shopping Airport last year. I set up a great landing. I had a great flight path, stabilized approach and everything. And I start to fly over this airport parking lot, and suddenly it's like the air kicks me in the ass, and I can feel the plane just taking off, and I'm sticking forward, and the plane's doing this, and then suddenly I go from this parking lot over a cold lake, and so the air stops rising above that and starts sinking down into the cold lake. And suddenly this forward stick turns into a lot of forward stick, and I look and all I can see is ocean. It's important to consider the fact that different areas of the ground are going to do different things to the air, and to adjust your planning accordingly. For instance, ground will vary its temperature a lot during the day. Water will stay about the same temperature all day long. So that means, did I see a question there?
Yeah, hey Chuck, I have you on mute, and we couldn't exactly see your questions. If you want to come off mute or type it in.
Oh, I can't see that. That's a little thumbnail for me.
It's a little small, Chuck. So if you want to type it into the chat, if you can. and we'll go from there. All right, Chuck, we'll keep working on that, and Andy, as soon as I get his question, we'll come back to it.
No worries at all. No worries at all. I'm running a little bit behind because this is a big presentation. Weather theory is a big
It's
subject. So
so,
let's
worth it, man. Keep going.
the ground changes its temperature during the day. Water tends to stay the same temperature all day long, approximately. So that means that during the day, the ground is going to be warmer than the water. So the air is going to rise above the ground, fall on the water. We call that a sea breeze because as the air rises here, something needs to fill that vacuum. And as the air cools down over here, it displaces the air this way. So the sea breeze during the day floats in from the water and brings that wonderful briny saltwater smell when you're close to the ocean. Of course, at night the opposite happens. The ground has become cold, but the water is still the same temperature. So now, the thing goes the other way. So it sinks down over the cold ground, rises over the hot water, or the warmer water, and again, the warmer air goes over here, falls down, displaces air that goes back here. So it's this cyclical motion all over again, and we call that a land breeze. So if there's a sea breeze during the day, there's going to be a land breeze at night. If you guys are doing night VFR or whatever, it might behoove you to understand that if the wind's always blowing from the west in a certain place next to a lake, after dark, most likely it's going to blow east.
So Marion has a good question, and he says, how does ground transfer heat to the air? And I think he's talking about the mechanical process. How do you heat from the ground into the air?
Okay, well, there's two things that can happen. Above all, we have something which we in physics call black body radiation. Now, black body radiation sounds like a complex concept. Basically, all that it means is that a hot object, whatever it is, whether it's a hot pocket or the surface of the planet, it gives off radiation to signal its heat. That's why we can see things in an infrared camera. Those cameras that police helicopters use to find people who are running away, or the camera that the Predator had in the Arnold Schwarzenegger movie that'll give you red for heat and blue for cold. Well, the whole reason for that is that hot objects exude an infrared radiation. They radiate in infrared. And basically what the ground does is it takes this visible light and energy from the sun, and it stores it, and then it gives it off as infrared, because the ground doesn't glow. It doesn't give off light that we can see. It's not visible light. It's infrared radiation. And this infrared radiation interacts with the air particles and kind of gives them a push. It goes into the air molecule, and it energizes the air molecule and gives it more energy. And as it gives the air molecule more energy, these little, you can think of them as dumbbells or barbells of, nitrogen and oxygen, they start to shake around, and they have a lot of energy. And as they do that, they start pushing on their neighbors, and their neighbors start pushing on their neighbors, and the whole air mass kind of becomes energized because of that. So it's basically this infrared radiation that the ground gives off at night. I hope that's a sufficient explanation.
I think so. It's actually a mechanical exchange of heat between the ground and the air, right?
Yeah.
Mm-hmm. Don't see a follow-up, so please continue.
Cool. So we talked about pressure, density, temperature. One word left: moisture. Moisture and humidity. The atmosphere contains it in all sorts of forms. We've seen snow, hail, we see fog, we see clouds, we see all sorts of humidity in the air. The air always contains invisible humidity as well, invisible water vapor. Something I wrote in big capitals over here: water vapor is not steam. We tend to think of steam as that white stuff that exists in a steam room. Water vapor is not that type of wet steam. Wet steam is actually liquid water. It's liquid water in tiny little droplets which are suspended in the air. It's not water vapor. Water vapor is a gas. It's an invisible gas. And so the air all around us always contains water vapor. If you want proof of that, think of your cold glass of Coca-Cola on a hot Florida day, and think about the condensation that comes on the outside of that glass. Well, you don't see that water in the air until it condenses on your glass, but trust me, it was there in the form of invisible water vapor which condensed on the surface of the glass. So water is present in all of its states in the atmosphere: liquid, vapor, and ice in the atmosphere at all times. And it's the transition between these states which make weather really interesting. This happens because of something we call relative humidity. Now, air can hold a certain amount of invisible water vapor, but it can't hold an infinite amount. There is such a thing as full air, air that cannot hold any more water vapor. And once it reaches this state, well, all the other water has to find some other way to exist in, some other form to be in, whether it's liquid or whether it's solid. If it falls down as hail or materializes as fog, it needs to find something else to do with itself because it can't stay there. One other thing, the amount of water vapor air can hold varies with the temperature of the air. So hot air can hold a lot more. It has a lot more luggage for this water vapor. And as it gets cold, it kind of scrunches up and it kind of shrinks together just like all of us do. And it doesn't, it can't really fit quite as much of it in its pockets. And if it's got way too much already, if it's all laden and it starts shriveling up because it's cold, well, it's going to start spilling out of its pockets. And it's going to start doing something else than being invisible water vapor. It's going to start being liquid. It's going to start being solid. It's going to start falling out all over the place, all over our cars and our driveways. If you're in Stockholm over here, snow. If you're in Florida, rain. It's going to be a piece of bad news. So if we cool an air mass, it'll reach a certain temperature where basically it can't hold any more liquid. It can't hold any more vapor because the vapor will become liquid. We call this temperature the dew point. If you've seen a METAR, you'll see that temperature dew point spread. They'll say temperature 51, dew point 48. Well, what the hell does that mean? Temperature 51, dew point 48? Well, that means that if this 51-degree air reaches 48 degrees, it'll be full. So if it reaches 47, you're going to start to see, fog. You're going to start to see rain. You're going to start to see some sort of luggage spilling out of its pockets. How far the current temperature is from the dew point and the direction in which this temperature goes can tell you a lot about the risk for visible water vapor, which is fog and clouds and so on. So if, for instance, you have a 51 to 48 degree situation, and you're in the evening and temperatures are going down, and there's only a 3-degree spread, I wouldn't go flying, because those 3 degrees, they're going to disappear like that as soon as the sun goes down, and that means that all that moisture in the air is just going to go visible, and boom, you're going to be fogged in. So the dew point temperature spread, along with the direction the temperature is going in, is going to help you make the go or no-go decision. So one of the ways in which moisture can become visible is fog. If warm air comes in over a cool lake, this cool lake is going to start to cool the air. And as the air starts to get cool, it's going to shrink its luggage and it's going to become full. And the luggage is going to become full and it's going to become overfull and it's going to start to overflow this water into visible liquid form. And you're going to start to see fog. Same thing if you have cool air, which is dry, and goes over a warm lake, it's going to pick up moisture and it's going to start, filling up its luggage. So any temperature change from there, it's going to have a lot of an easier time, disgorging that as something visible. We'll get to that in a second. There's also radiation fog. So if the ground gets cold at night and you have air which is moist and it comes in over that, that cooler ground, well, that's going to cool the air down. It's going to cool it past its dew point, and boom, you're going to see the moisture in that air. It just becomes visible. It's like turning off a cloaking device. The same happens as we learned with the lapse rate, air gets colder as it rises. So if you have moist air, which is warm, and it starts going up because the ground is hot, and it starts to go up, and it starts to go up, and it starts to, lose temperature, 4 degrees Fahrenheit per 1,000 feet. Remember, guys? And that, temperature dew point spread is going to start shrinking, and eventually it's going to get to the point where 4 degrees times, 1,000 feet, it's going to reach that dew point temperature, and boom, turn off the cloaking device, and the moisture in the air is just going to go visible. And that's how clouds are born. That's exactly what happens. Wow. And if you want to calculate how high the clouds are, the cloud base, you basically take the temperature dew point spread and divide it by 4. That's your cloud base in thousands of feet. So if it's 85 degrees out, dew point of 50, that's a 35 degree spread. 35 divided by 4, it's about 36 divided by 4, it's about 9. So it's about 9,000 feet. So cloud base is going to be 9,000 feet. You don't even have to look up at the sky to know where the clouds are going to be. All you have to do is look at the temperature dew point spread, divide by 4. That's your cloud base. Little meteorology tricks from meteorologists here.
Wow.
But I do definitely want you guys to look at METARs, to look at TAPS, and go experience that weather, okay? Because it's one thing to read 2,000 feet, and okay, 2,000 feet, well, what's that? Well, go outside, look out the window, learn what what is broken, what is scattered, what is overcast, how scattered is scattered, what is visibility of 1 mile, what is a visibility of 3 miles. Try to figure out, some weird taps that you haven't seen before, and just go out into the nature and see what that looks like, and let that help you make decisions in the real world later on, because you'll go like 6,000 feet. Yeah, I know what that looks like. And that'll help you inform your decision-making process as well, because that's all this is. This is ammunition for your decision-making process.
Hey, Andy.
Okay.
We talked about 4 degrees Fahrenheit, but what about Celsius? Is it the 2?
2, yeah. So 2. That's also in the notes in the spreadsheet in the presentation. So it's about 2 degrees Celsius, about 4 degrees Fahrenheit. That's an approximation, but 4 usually works in most situations. It varies between about 3.5 and 5.5, but 4 works most of the time.
Dry, wet, yep.
That's it. Dry, wet, altitude, so on. So we have the knowledge of the pressure, the density, the temperature, the moisture. Let's put this together, shall we? Because it's time for me to go home. We should have been done with this 5 minutes ago, and we all have stuff to do. So let's start tying this up. Let's talk about these masses of air. Okay, so we talk about air masses. We talk about a large body of air, which sits over a region of the world for long enough that it basically becomes that region of the world. If it sits over Alaska, it becomes like Alaska. It becomes dry and cold. If it sits over the Sahara Desert, it becomes warm and it becomes dry. If it sits over the Amazon rainforest, it becomes very wet and very warm, and so on. And these air masses, we call them polar, tropical, basically because they either come from the polar regions or the tropical regions. Maritime or continental. Maritime comes from the water. Continental comes from land. So that's all that means. And if we look at a picture of the air masses here, you see the United States gets an influx of air masses from all sorts of directions. You have maritime tropical air here, maritime polar air. So that's basically polar air coming from water, tropical air coming from water, tropical air coming from land. Again, tropical air from water, polar air from the water, polar air from land, and that's Arctic air up here. That's like the super cold stuff. And all that means is that if it's a continental polar mass, for instance, it's going to be cold and dry. That's all it means. If it's maritime and tropical, well, it's going to be hot and wet. That's all it means. So you don't have to hang yourselves up on continental, polar, Arctic, whatever. Just think about what are those regions like, and just realize that the air that comes from those regions is going to be like those regions. So air that comes from the Amazon rainforest is going to be hot and wet. Air that comes from Alaska is going to be cold and dry. That's all that means. I'm going to give you guys a little bit of a case study here. Here in Sweden, we have something called snow cannons. This is very similar to the Great Lakes blizzards. The snow cannons are a very particular type of storm which come in from Finland. They start to move in over here, and if at the start of winter, this body of water here, the Gulf of Bothnia, if that isn't frozen, then we're in for a very snowy winter. Because what's going to happen is this air from Finland.
Can you pan camera right? There we go.
I just did. This air from Finland is going to be dry and cold. And because it's dry, as soon as it hits this water, it's going to start drinking. It's going to start drinking its fill. It's going to fill itself up with moisture because it wants to do that. Air doesn't want to be dry. It wants to contain water vapor. It's going to drink itself full. It's going to reach the coast of Sweden, and then it's going to start to go up the coastline, gain altitude. And you guys know what happens when it gains altitude, right? It starts losing temperature. And as it starts losing temperature, that temperature dew point spread pancakes out. And what does it do? It dumps out snow like you would not believe along the coastline. And of course, everybody inland is fine because once the air has dumped all of its moisture out, well, then it's just cold, dry air again. And then, you know, it's going to be cold, but it's not going to be very snowy. But over the coastline, my goodness. So we call it a fortunate winter when this Gulf is frozen before this air mass starts to move in. Because if it's frozen, can't take on any moisture, so no snow. Very important thing in making go, no-go decisions in eastern Sweden, which is where I live, is something like that. And if you guys live near the Great Lakes, you guys are going to feel the Great Lakes every step of the way. You guys are going to have to look at Lake Erie all the time. You know, basically, what is the air like? Is the air coming from Canada? Because if it's dry Canadian air coming in over Lake Erie, forget about it. There's going to be so much snow you won't even believe it. You won't be able to get your car out. So it's just, you know, a question of making decisions based on stuff like that. As the, you know, moist air reaches the coastline and starts going up, temperature dew point spread goes down to 0, and it dumps out its moisture as snow.
Yeah, I live in Pittsburgh, so we live and die by Lake Erie.
Yep.
Yes.
I understand. Okay, so when these air masses basically interact with each other, when this bubble of air meets this bubble of air, well, what's going to happen? If this maritime polar air, which is like, you know, cold and wet, meets dry, hot air coming in from the other direction, and they meet, what's going to happen? It's not going to be a meet cute. It's not going to be a handshake. There's going to be a front. The front line between these two warring quantities of air. So an air mass which passes over something which is hotter than it, it's going to be heated from below. If it passes something colder than it, it's going to be cooled from below. It's going to start to take on the characteristics of the ground that it's passing over, and it's going to change accordingly. So you're going to see the weather change as, you know, a front moves in. That's a recipe for weather that, you know, is going to change by the hour, especially a cold front comes in. Have you guys ever looked out and just seen a wall of blackness approach? That's a cold front. Those are incredibly dramatic things. So we're going to talk about fronts for a little bit. We talk about, you know, cold fronts, warm fronts. We have stationary fronts, which we're not going to talk about at all because they're not really interesting. They're just fronts that stay over an area and dump out their moisture there. And occluded fronts, we're going to go through why these occur. But warm fronts and cold fronts are your main types of fronts. And basically a warm front is when a warm piece of air is displacing a cold piece of air. And a cold front is when that cold piece of air comes back and displaces the warm air. Or a new piece of cold air comes in from behind and displaces the warm air. So it's all about, is the air coming in hotter or colder than the air going out? If it's hotter, it's a warm front. If it's colder, it's a cold front. A warm front is basically this, okay? So the warm air comes in, and because the area over here, I love standing like a meteorologist. It's just so cool. I wish I had one of those green. As the cold air is here, and the warm air is coming in from this direction, because hot stuff rises and cold stuff sinks down, the warm air isn't going to scrape along the surface. It's going to put itself on top of this cold air like a blanket. It's going to basically pull itself over the cold air like a duvet, and it's going to have this lovely fluffy cloud structure all along the way. So you can see a warm front coming from, you know, hundreds of miles away, because it's already there. It's not something you're waiting for. It's already there. It's just that it's on top of this cold air and it hasn't really reached you yet. And eventually, over a period of sometimes even days, this will, you know, roll in, and you'll start to see this cloud base go down with each successive day until you get the actual warm front here. But the actual interesting weather activity is already over here. And if you look at this map, that's about 300 miles away from where the actual air mass is hitting the ground. So warm fronts are very, very long, very, very large things. I'm going in the wrong direction here. And what happens when this warm air comes in over the cold air is, you know, this was cool air, and as, you know, stuff gets heated by the ground, it can start to climb, you know, like these bubbles, like in the lava lamp. But when the warm air comes in, it kind of pulls itself like that duvet over the cool air. And suddenly this layer of really warm air, it won't let this air rise, because even if it's getting a little bit warmer so that it can start to rise, well, this is warmer still, so it can't pass this area. It really lays itself like a blanket. So all the smog, all the particulate matter, all the, you know, exhausts, everything is just trapped there. I grew up in a city called Sarajevo in Bosnia-Herzegovina, which was surrounded by mountains. And what happened on a day like this, if you had a warm front go by and you had a mass of warm air, you basically could climb the mountains and look down into the city, and it would look like a bowl of cereal. You know, it would just look like milk with these little buildings sticking out of it, like Rice Krispies. It's because this warm air is on top of the cold air, basically killing its ability to make these bubbles, these lava lamp bubbles. What happens in this region is really interesting if you're flying, because these two areas of wind, the cold air here and the warm air here, they might have completely different wind directions. The wind in one could be, you know, almost 180 degrees compared to the wind in the other. And the region between these two masses of air is going to be bumpy, is going to be super, super bumpy. And you are going to have, you know, a certain headwind here, and as you're coming down, you're going to find an incredibly turbulent area full of, you know, little whirlpools and so on, vortices. And as you come down, you might find that you're in a tailwind or a crosswind or whatever. If you're really unlucky, ATC will put you right here. They'll just say, you know, climb and maintain 3,500 feet, whatever, and then you'll be here.
No.
And that's, you know, it's time to call for a different altitude and just say, I'd like to avoid the wind shear. But that happens because of that, you know, one area of air which is just lying on top of the other. And if the wind is blowing differently, of course, in that area in between them, it's going to be really mixed up.
But what if there is a?
Please go ahead.
Yeah, if there's a PIREP at that shear zone, you're certainly that you're going to let ATC know we got some problems at this particular flight level, and they should know from there on. Certainly, if other PIREPs come in saying the same thing under the same conditions, that they now know that whatever limited their weather sensing features are, we've got actual reports up here. Is it up their responsibility to pass that on?
For sure, guys. Never hesitate to make a PIREP. That is, you know, ATC is trying to keep everybody alive, and meteorologists on the ground have computer models. They have measuring equipment, which is in the terminal areas, but nobody can tell you what the air feels like at 4,433 feet, except the guy who's at 4,433 feet. So it is, I mean, I would go so far as to say it's your responsibility, but definitely, if you do have an observation to make, do make it. Make PIREPs. PIREPs keep people alive. So definitely, guys, don't hesitate in any situation. A warm front, this duvet blanket, it looks like this. Okay, so this is basically what a warm front is. It's this little area of visible air, and then you got this blanket of clouds, which is all around you, just overcast. And when these things dump out rain, they don't dump out thunderstorms like a cold front does. This is that rain that lasts for days, that horrible London, England drizzle that just goes on and never gets to the point. It's just, this is horrible flying weather. I hate it when warm fronts come in, because that just means 3 or 4 days of just hazy, bad, foggy, drizzly weather. And if it's winter, that drizzle turns into icing. Just forget about it. Cold fronts, on the other hand, happen when a cold mass of air comes in to displace a warmer mass of air, okay? And that looks a little bit like this. But because it's cold, it's not going to lay itself like a blanket like the warm air did. It's cold. It sinks underneath the hot air, and it kind of comes in scraping along the ground and pushing all of this hot air up as it goes along. Now, as it does that, it pushes this hot air up, and you guys know that as it pushes the air up, the temperature decreases. Temperature decreases means that temperature dew point spread starts to decrease, and when it reaches 0, it pancakes, and you start to see this phenomenon. Okay, so as a cold front is approaching, you're going to start to see this warm air getting pushed up, and you're going to start to see these cumulus clouds. So they're going to be cumulus, towering cumulus, cumulonimbus clouds. But as you can see, all the important weather activity is actually really close to the front itself. So they're dramatic, they're fast, but they also pass quickly. So a cold front is one of those things where, as I said, you walk out and you just see a wall of black approaching. It's okay, you don't have to cancel your flight. Sit tight for 4 or 5 hours, let it pass. Because as you can see, behind the cold front is nice, clean, flyable air. Some of the best flying you'll ever do is going to be directly after a cold front passage. And please, for the love of God, guys, do not try to fly under a cold front. Do not try to fly above a cold front. If you see a squall line that's 100 miles wide, either go really out of your way to go all the way around it, or just wait for it to pass, because you cannot make it if you try to go above it. And there's one of those huge cumulonimbus clouds that goes tens of thousands of feet into the atmosphere, which you can't reach. And going under here is a really bad idea, because the rain is going to bring such downdrafts that it might cause you to lose control of your plane. So wait it out. Trust me, it's worth it. Cold fronts are fast, they pass quickly, and after they pass, you'll get some of the best flying weather in the world. Cold front weather looks like this. This is what happens when a cold front passes. You get this cumulonimbus, towering cumulus clouds. I call them Simpsons clouds because they kind of look like the clouds from the intro to The Simpsons. Basically, what these clouds show me is that, like, if we take a look at this lovely little, shaped cloud here, this is basically just a bubble of air which is rising, and it reaches a point where that temperature dew point spread is 0, and it becomes visible. But this is the bubble. This is the lava lamp bubble, guys. You can see it right there. That's the lava lamp bubble, and you can see, like, if this stays over the same parking lot, it's just going to grow taller and taller. It's going to blow itself up like a balloon. If there's wind and it moves on, you're going to see that in the same space, you're going to see another bubble pretty soon. It helps you identify the areas where you're going to see that thermal turbulence. So when I fly and there's a cold front that's just passed by, and I have this lovely cold air mass in front of me, I look for clouds like this, and I go like, well, that's going to be a thermal, so I'll fly around it. Or if I had been in a sailplane, I'll go directly under here, because that'll give me an altitude boost. This is basically the cloaking device being turned off of one of those lava lamp bubbles. So that's exactly what this is. I love these things. It's so rare that you see weather truly become visible like that. Now, one thing I told you, warm fronts move pretty slowly. Cold fronts move very fast. What happens when a cold front catches up to a warm front? I mean, that's got to happen, right? I mean, if this is really slow and there's a cold front behind it that's moving, you know, twice as fast, eventually it's going to catch it, right? And it does. It does all the time. It happens all the time. We call them occlusion fronts or occluded fronts. Cold fronts move faster, and they catch up with warm fronts, and you basically get one of these situations. So you get this massive air, which used to be here. This is the air that is being displaced. And here's the warm front. Here's that lovely duvet of you know, stratus clouds, which is going to pull itself up like a blanket over the air. But here comes the cold front with all of its weather as well. So you get this phenomenon where you first get the warm front weather, and then you get the cold front weather. And if you're really unlucky, this air is actually the coldest. So it actually starts to push up this air as well. So this starts to go up, and this starts to get colder, and this starts to decrease its temperature dew point spread, and then this starts to dump out its water vapor as well. So you get cold front weather from this, warm front weather on top of the cold front weather, and then you get a second cold front coming in. So occluded fronts can be incredibly dramatic, incredibly violent things. They can be very, very cool to look at, very, very cool to study, not very, very cool to fly through. So I would advise against this particular practice. If you see an occluded front, just realize, as I said, these fronts move by quickly. Once this air has passed, you're going to be back to Simpson's clouds and visible lava lamps, and just go buy your METARs and TAFs, and it'll be some of the best flying you ever do. I apologize if the latter half of this lecture was a little truncated and if I've gone a little quickly, but weather is a large subject. I mean, it took me 6 months to learn what I tried to tell you guys in an hour and 20 minutes. It's never going to happen, but I tried as hard as I could. This is it. Thank you very much for watching. And if you have any questions, I would like to take them right now.
Yeah, so we'll go ahead and open it up for questions, but man, great job, man. I'll tell you, we as instructors, and I'm just as guilty, tend to take a very fact approach to teaching weather. This was completely out of bounds. This was great. So thank you very much for taking the time. So I have some bad news and I have some worse news. So Andy can't join us for part 2 of meteorology. And the worst news is you're stuck with me. And now, after watching this, I feel very bad that I have to teach the second part of the class. So, so we'll go ahead and open it up for questions. But while we're doing that, I'll just tell you a little bit about what's coming up. On Tuesday of this week, we're going to talk about weather sources, where you get the information that Andy was talking about, how you can understand what the forecasters are saying, where you can go find out information. Next Sunday, we'll pick up with part 2 of meteorology, where we'll talk about bad weather. So what are the dangerous parts of weather that we need to avoid? Thunderstorms, fog, icing, those types of things. I don't see any questions. I really appreciate everyone hanging in there over time, but I think it was so worth it.
Yeah, you guys are super. I mean, this is if I didn't know this stuff already, my brain would have been full 40 minutes ago. I mean, this is an incredible amount of information to just dump out over you guys in such a short period of time. So brave and valiant of whoever managed to go the distance, definitely.
No, and
well, listen, thank you so much.
Yeah.
Can I say?
No, go ahead, Joe.
Can you hear me?
Go ahead.
Well, first of all, if you're not an instructor, you need to be. You've got a wonderful way of presenting the excitement that you obviously have for your subject. And being an instructor myself, I got to say, dude, you got to get yourself in front of folks and let them have the privilege of learning from you.
Well, thank you very much. That means a lot to me. Thank you.
That being said, well, I also lie a lot, so take that with a grain of salt. Uh, that being said, um, why does the high pressure area circulate in a clockwise manner, whereas the low pressure, as presented, seems to be circulating in a counterclockwise manner?
Okay, well, we'll go back to the relevant slide to that, so I can help you with illustrating that point. Let me just find it.
And is it really relevant?
It's relevant insofar as that it helps you make decisions with your flight path. Like as I said, from here you can basically
Oh,
decide
right, right, right.
where
The
your tailwind is going to be. So that it is relevant because
Gotcha.
of that. But it goes into the entire sort of Coriolis effect idea. Like if we go back to this picture, and I see that if I'm moving
Right.
north, if air is moving north in the northern hemisphere, it's going to veer off to the right into the rotation of the Earth, because it's got this boost from being all the way out here by the equator. It's moving at 1,000 miles an hour, so it's going to go off to the right. Now, if we look at what happens with a high pressure area, high pressure areas are areas that air is escaping. Okay, so if the air escapes a high pressure, it's going to get deflected to the right when it goes north. See what I mean? So if it goes north,
Okay.
escapes, it gets deflected to the right. It's because of course.
Okay.
If it goes south,
Okay.
it goes this way. So basically, the same thing applies for low pressure. If you just think about it as north motion, if it goes into a low pressure, it's also heading north. If it goes out of a high pressure and you think about it going north, either way, it's going to get deflected to the right. So it's basically the same
But
thing.
the bottom line, though, is understanding that flying between high pressure and low pressure can give you tailwinds if you see where those pressure areas are.
Absolutely. This is why I took up these isobar lines, which basically help you make that determination. Wind is going to be parallel to the isobars. So if you're flying through this area, you're going to know basically the wind is always going to be between these, and it's going to be going in the direction that they're going. So if you're flying north to south, well, that means you're going to have a crosswind the entire way. If you're flying this direction, it means you're going to have a tailwind the entire way. So basically, it helps you plan your flight by just looking at the weather picture, and already just by seeing where the high and low pressure regions are, you can already then just tell if you're going to have a tailwind, a headwind, or a crosswind, what's going to be going on. You can even tell with regards to your airport what runway it should be taking off from, because if you see the isobars and you see which side the high and the low pressure is on, you know already which direction the wind's going to be blowing from. You don't even have to look at the METAR. You can just go, well, today is going to be a westerly wind, so I'll pick runway 27, and then you look at the METAR and go, ha, I'm a genius,
Okay, so can we say there? What I'm taking away from this is I'm flying in. First of all, let me let you understand. I'm an old fart that'll never be able to afford to get my private ticket or my multi-engine or my ATP, but I've got about 10, 15 years to live, and I've been an aviation nut for ever since I was a child, and I'm learning as much as I can. So that's me. And the bottom line is I'm flying tube liners. I'm also flying in my Lancer Legacy Experimental. And the bottom line is that I'm getting pretty damn good representation of the weather through Active Sky 16, and I have actually broken my joystick trying to get out of weather that I purposely put myself into to test out Active Sky.
Yes,
Bottom
sir.
line is, wouldn't it be it seems to me that it would be super helpful if we got out of our tube liners, got out of our Lancer Legacies and TBM 850s, and got into soaring for a while to better understand what we're really talking about here.
Yeah. My CFI, when I was getting my license, my CFI was a sailplane flyer originally. So he had that Dale Earnhardt thing. He could see the air. It was amazing, and he taught me many of these things, like looking at cumulus clouds and basically seeing them as these rising columns of air, looking for birds who are just, circling around the thermals, stuff like that. Just things that sailplane pilots pick up on that the rest of us are completely oblivious to as we power ourselves through the air. But I would say that experiencing it in a sailplane is one thing. I would also encourage everybody who has a sim at home, flight simulator, to do the same thing. As I said, if you have a METAR, any flight sim worth its money these days is going to be able to replicate real world weather. So if you want to take a look at, on a particularly cloudy day, or, if there's some frontal activity, go into FSX or X-Plane or whatever, load up the current METAR in your position and fly through that weather. See what that's like. See what it's like to fly under that squall line, and see what I'm talking about when I say it can be done. I think the sim could be used very well as a weather teaching technique, because we use computers to model weather. That's how we develop our forecasts. We use supercomputers, and the computer in your FSX can do a very good job at approximating what weather systems behave like. So I would definitely use the sim more when teaching weather behavior.
Yeah.
Okay. Well, the last question is, how the hell do you have a Midwestern accent and you live American accent and you live in Sweden?
It's very interesting. I do hear Midwestern a lot. I did spend some time in Ohio. But that was mostly recreational, some educational times as well. It's a long story. My dad is a professor of the English language. He raised me bilingual, so I have no affiliation with the United States. Never been a citizen. Never been anything else but a vacationer there. And the accent is just something that happened organically as I was growing up. Many thanks to my father, because it's brought me a lot of advantages in life. And that's that basically.
Well, as an actor who loves accents, I am blown away, and tell your dad he did a hell of a job.
Thank you very much. I will definitely do that.
Yeah. So,
well, guys, if that's it, let's round this up then.
Yeah. So the feedback
thank you
has been so positive in the chat room. So thank you very much. I mean, I've never had someone, with all due respect, explain the Coriolis effect like you did. The idea of a left crosswind on landing is something I learned today. So absolutely fantastic job. Thank you so much for joining us. And I really look forward to having you teach more sessions in the future.
I would look forward to the opportunity. Thank you for having me. Yeah. Well, guys, have a great evening, and thank you for having me today.
All right, have a good evening. I'll talk to you later. See you on
terrific.
Tuesday. Bye-bye.
And thank